A skyscraper does not go up floor by floor the way it looks from the street. At any moment on a tall building site, 6 completely different trades are working on 6 different levels of the same tower at once, and the whole schedule is a race to get the building watertight before the weather and the money run out. Long before a machine arrives, the site has already been investigated in enormous detail. Geotechnical engineers drill boreholes down through the ground, sometimes 50 or 100 meters, pulling up cores of soil and rock at intervals, and testing every one of them for strength and compressibility. They are trying to answer a single question: how deep do we have to go before we find something that will not move? Because a tall building is not really a problem of holding weight up. It is a problem of holding weight still. Any building will settle slightly as it loads its foundation. On a house, a few millimeters of settlement is invisible. On a 300-meter tower, if one side settles 15 millimeters more than the other, the top of the building leans by a noticeable amount, lifts stop running true, facade panels bind, and the cladding joints open up. So the geotechnical report does not just say what the ground can carry. It predicts how much the building will sink and, crucially, how evenly. Alongside that, wind engineers are already at work. A model of the tower and several blocks of its neighbors is built and put in a boundary layer wind tunnel, where fans generate a wind profile that mimics the real turbulence of a city. They measure not just the force on the building, but the way it sheds vortices as the air peels off the corners. Those vortices are what make a tower sway from side to side, and if they shed at a rhythm that matches the building's natural frequency, the sway grows. Almost every unusual shape you see on a modern supertall exists because of that test. The tapers, the setbacks, the twist, the openings cut through the top. The Burj Khalifa's spiraling setbacks confuse the wind so it never settles into a single rhythm around the tower. Engineers call it confusing the wind, and it is a design decision worth more than any amount of extra steel. Then the digging starts, and on a constrained city site, the excavation is often the most dangerous and most technically demanding phase of the entire job. You cannot simply dig a hole with sloped sides, because the neighboring buildings, roads, and underground services are right at the boundary. So before excavating, crews build a wall down through the ground around the whole perimeter. Often that is a diaphragm wall, a trench cut in panels by a specialist grab or cutter, held open by bentonite slurry so the sides do not collapse, then filled with a steel cage and concrete placed from the bottom up so it displaces the slurry. Panel by panel, a continuous concrete wall is built underground before the soil in front of it is ever removed. Once the wall is complete, the excavation goes down inside it, and as it descends, the wall is braced, either with huge steel struts across the hole or with ground anchors drilled out and tensioned into the soil behind. On some projects, engineers use top-down construction, where the ground floor slab is cast first and the basement is excavated underneath it through openings. So the permanent slabs themselves brace the walls and the superstructure can start rising while the basement is still being dug out below. It is complicated and expensive, and on a tight program it can save many months. At the bottom of the hole, the foundation itself is usually a piled raft. Board piles are drilled deep into competent ground, and a thick concrete raft ties them all together into one enormous structural element that spreads the tower's weight and, just as importantly, resists it tipping. The scale is hard to picture. Under the Burj Khalifa, there are 192 piles, each about 1.5 meters across and 43 meters deep, under a raft 3.5 meters thick, holding a building that used 330,000 cubic meters of concrete in total. That raft pour has to happen in one continuous operation, sometimes running more than 24 hours with a truck arriving every couple of minutes, because a cold joint in the middle of the foundation is not acceptable. Engineers even chill the mix with ice or liquid nitrogen, since that much curing concrete generates so much heat that the inside would crack itself apart as it cooled unevenly. Now the tower starts to grow, and the first thing to rise is almost always the core. The core is the vertical spine in the middle of the floor plate that holds the lifts, the stairs, the risers, the plant shafts. Structurally, it is the building's backbone, a hollow concrete tube that resists most of the wind load and stops the tower twisting. It is built ahead of everything else, and it is built with a self-climbing formwork system. Jump form is the most common. Hydraulic jacks lift a whole platform of formwork and working decks up the outside and inside of the core one story at a time. Crews tie reinforcement, close the forms, pour, wait for the concrete to gain enough strength, then jump the rig up and do it again. A typical cycle is 3 to 5 days per floor, and on a good job with a big enough crew it can be pushed under 3. The alternative is slip form, where the formwork never stops. It creeps upward continuously, a few hundred millimeters an hour, while concrete is placed at the top and emerges cured at the bottom. It is relentless, requires round-the-clock crews for weeks on end, and produces a seamless shaft with no joints at all. Getting concrete up there is its own engineering problem. At height, you cannot rely on a crane and a bucket. Concrete is pumped, and pumping it vertically hundreds of meters means the pump has to overcome enormous pressure in the delivery line while the mix must stay fluid enough to move but strong enough to perform once placed. On the Burj Khalifa, specially designed high-pressure pumps pushed concrete to a record 606 meters. It was pumped at night, when the Dubai air was cooler with ice in the mix, to stop it stiffening in the pipe on the way up. As the core climbs, the floors chase it up from below. In a steel frame tower, columns and beams are bolted together into a frame and steel decking is laid across the beams. Then a thin concrete slab is poured onto the decking, which acts as both the mold and the reinforcement. In a concrete frame tower, columns are cast and slabs are formed and poured floor by floor, often using flying forms, whole table-sized sections of formwork that a crane lifts straight out of one floor and flies up to the next. Either way, the sequence is the same. The core is highest, the structural frame is a few floors below it, and everything else follows below that. Doing this work at height depends entirely on the tower cranes, and the cranes themselves have to grow. A tower crane can be freestanding only to a limited height. Beyond that, it is either tied back to the building with steel collars every few floors, or it is climbed internally, sitting inside a lift shaft or a hole in the slabs, and jacking itself upward through the structure as the building rises around it. The crane is the single most contested resource on the whole site. Every trade needs it. Its hook time is scheduled in 15-minute blocks, and a crane sitting idle is one of the most expensive things on a construction program. Which raises the obvious question: how does the crane get down at the end? Usually a smaller crane is assembled on the roof to dismantle the big one, then a smaller one again to dismantle that, until the last piece is small enough to be taken down in the building's own service lift. Following a few floors behind the structure comes the facade, and this is the moment the project starts to make money. Modern towers use a unitised curtain wall. The facade is not built on site. It is manufactured in a factory as complete story height panels, each with the glass, the frame, the insulation, and the seals already installed and tested. On-site, panels are hoisted up, guided in by a small crew, and clipped onto brackets cast into the edge of each floor slab. A good crew can install dozens in a day, and unlike site-built cladding, quality is controlled in a factory rather than on a windy platform 300 meters up. Those brackets have to allow movement. The building sways in the wind, the slabs deflect as they load, and the concrete frame slowly shortens over years as it shrinks and creeps under sustained load. In a supertall, that shortening can add up to 100 millimeters or more over the life of the structure, and the columns and core shorten by different amounts. So the facade connections are designed to slide and rotate, and the joints between panels are sized to take that movement without the glass ever going into compression. The whole schedule points at one milestone: getting the building envelope closed. Until the tower is watertight, the interior trades cannot start properly, because you cannot install plasterboard, flooring, or electronics in a building that rains inside. The moment a section is sealed, the site can be heated, dried, and handed over floor by floor to the fit-out crews, and suddenly the interior work of dozens of floors can happen in parallel. That parallel work is what really defines a tall building program. Walk up a tower under construction, and you pass through the whole history of the project in a few minutes. At the top, formwork and rebar and wet concrete. A few floors down, steel erectors and decking. Below that, the facade crew clipping panels on. Below that, mechanical and electrical crews running ductwork, pipework, cable trays, and sprinkler mains through the ceiling void. Then partitions, then ceilings, then finishes, then commissioning. 6 or 7 distinct building sites stacked vertically, all sharing one set of hoists and one crane, and all sequenced so that nobody is standing under anybody else. The services alone are a huge engineering exercise. Water cannot simply be pumped from the ground to the top, because the pressure at the bottom of a single continuous column of water 300 meters tall would burst the pipework. So the building is divided into vertical pressure zones, with plant floors partway up where water is collected in tanks, repressurized and sent on to the zone above. Lifts have the same problem in reverse. A single lift shaft running the full height would need an enormous, extremely heavy cable, and it would be intolerably slow to use. So tall buildings use sky lobbies, where high-speed shuttle lifts run express to an interchange floor and passengers change to local lifts serving their zone. It also lets several lifts share one shaft footprint at different heights, which matters enormously, because lift shafts consume floor area on every single floor they pass through, and floor area is the entire commercial point of the building. Then there is the sway. Every tall building moves in the wind, and it is designed to. Stiffness is expensive and heavy, and past a certain height it is cheaper to let the building move and control the movement instead. The engineering target is usually not strength at all. It is comfort. People cannot feel a building deflect, but they can feel acceleration, and if the top of a tower accelerates back and forth too sharply, occupants feel motion sickness even though the structure is nowhere near distress. So super tall towers are fitted with dampers. Some use a tuned mass damper, a huge weight, sometimes hundreds of tons of steel or a tank of water, suspended near the top and tuned to swing at the building's own natural frequency but slightly out of step with it. So its inertia pushes back against the sway and bleeds the energy away. Others use dampers built into the structure itself, or slosh tanks where moving water does the same job. Between the aerodynamic shaping, the core, the outrigger structures that tie the core out to the perimeter columns, and the dampers, the top of a supertall might move half a meter in a serious storm, and the people inside will not notice. When the last structural element goes into place, the building is topped out, and traditionally a tree or a flag rides up with the final beam, a superstition inherited from Scandinavian builders. It is a real milestone, but a misleading one. Because when a tower tops out, it is usually only around halfway through its program in terms of remaining work and cost. The facade still has to be finished, the interiors completed, and then the entire building has to be commissioned. Commissioning is the phase almost nobody thinks about. Every system has to be tested in concert. Fire alarms, smoke extraction, sprinklers, pressurized stairwells, emergency power, lift recall behavior in a fire, the building management system that runs it all. Smoke tests are performed, pumps run at full load, generators started on simulated power failure. Only after all of that does anyone get a certificate to occupy. In total, a serious tall building takes 3 to 5 years from breaking ground, and the tower that stood empty for months at the end was not delayed by construction. It was being tested. So the next time you watch a skyscraper go up and it seems to stall halfway, remember it almost certainly is not stalled. The visible part, the structure, has simply finished, and everything else, the part that actually makes it a building, is happening behind the glass. Follow for more construction facts hiding in plain sight.